Hi everyone, it's been about 5 months since my last video. I have been busy with work and other things. Also, the project I'm presenting in this video took a lot of time. So just yesterday, I finished this addition to my personal C libraries project, and I think it's pretty cool. So thank you for clicking, and I hope you enjoy. Okay, so if you saw the title of this video, you could probably guess we're going to be talking about RPC. If you don't know what RPC is, I wanted to do just a very quick explanation now before we start really coding. So RPC stands for Remote Procedure Call. And while there are probably many nuances to this topic, I think at face value it's pretty simple. The idea is that we want a function which we can call on our local machine that looks just like any other function, but behind the scenes is actually sending a request and waiting for a response from a remote server of some type. So for example, if we had a function do work that maybe takes 2 arguments, and normally we would just do some sort of calculation on our machine like this, what we're going to do instead is on the inside of do work, what we're going to do is we are going to serialize our arguments, send a request, wait for a response, deserialize, and return result. So the specifics of these things, of these steps, are going to be very complex and would be extremely annoying for the user to have to figure out how to work with, okay? But the beauty of RPC is that if we use it correctly, the user can be sending requests to backend servers and other computers without even realizing, right? And they could write their program just like any other program. That's the idea. And that's my quick little explanation. So why don't we start actually coding? All right, before we actually do RPC, I wanted to talk about how my library does serialization. If you're unfamiliar with serialization, it's the process of taking kind of a complex value in memory and translating it into a continuous sequence of bytes, such that you could take those bytes and reconstruct the value. That might not seem that might seem a little confusing at first. Like, doesn't a value in memory already exist as bytes? Why can't we just write those bytes to the buffer? Why can't we just write those bytes back to back to back? Like, wouldn't that be enough? And the answer is no. So like, I could give an example of like, maybe I have a struct person, and a person has a name. I'll say first name, char star last name, and I could say uint age. And let me do this. Let me do type def. And you might say, if I had a person like this equals, first name equals, I'll say Bob, last name equals Smith, age equals 23. And now I also have this buffer up here, right? So what you might think is if I wanted to take this structure and write it as a continuous set of bytes to this buffer, what I could do is I could do something like this, or I could say, well, why don't I just take the buffer, convert it to a pointer to a person, and then write the value. Oh, whoops. There we go. write the value I've constructed. Wouldn't this be an easy way to serialize? And the answer is no, because the problem is that oftentimes when you work in C, you work with pointers. One structure will rarely physically contain all of its contents. It'll usually at some point contain some sort of pointer to another structure in memory, which has more information about the overall value, right? In this case, person, we have 2 pointers. We have first name and last name, right? They are not stored directly in our person structure. Rather, the address of each string is, and then the address is used to actually get the string later. So when we write our person to a buffer here, Bob, the text Bob and Smith are not being written to the buffer. What's really being written is the address of Bob and the address of Smith, which are somewhat irrelevant because these addresses are specific to the process that's running. If I were another computer and I got this structure in memory where it was 2 addresses followed by the age 23, well, those addresses I couldn't use. You know, I'm on a totally different computer, right? Totally different process. So this is why serialization is very important, and how we serialize does matter. So lucky for us, my library gives a mechanism for creating data of an arbitrary structure such that the resulting value can always be serialized. So if we go into the RPC library include directory, we can see what header files we have available to us. Right now, why don't we look at serial type and serial value? So if we went into serial type, we could see the types of values that my library supports. So basically, there's a bunch of integral types of varied width. There are floating point types. There's a string type. These all make up the primitive types. And then after that, there are the structure and array composite types. So a structure is just like it would be in C. A structure has a fixed number of fields, and each field can have its own type. The types don't need to match. An array can have any length, but every element in the array must have the same type. So those are the rules. If we wanted to create a value, we would go into serial value.h, and we could see all the constructors that are available to us. Basically, there is a special constructor for every primitive type, an array of every primitive type, and then the composite types I mentioned. So anyway, enough of that. Why don't we use it, because that would be a little bit more interesting. Okay, so why don't we start by recreating our person value, but instead of using the C struct mechanism, we're going to use our own like C RPC value constructors. So let's delete the structure, and we can delete the corresponding value. Now let's do C RPC value T star P equals new C RPC value. Let's do struct value VA. VA is for var args. All right, now let's provide each individual field. So I think there was an age, first name, and last name. So let's do new CHRPC B8 value. I think he was 23 years old. Then new CHRPC string value, Bob. New CHRPC string value, Alan. Cool. And you might have guessed this because all the functions start with the new prefix, but all these values are going to live on the heap. Also, these internal values will be owned by the resulting structure. So when we delete P, it's going to delete everything. That was by design, so you could use the constructor in this way safely. So let's delete our C RPC value at the end, P. And to confirm things are working correctly, let's do C RPC value to, or actually, I think it's C RPC value print. Yeah, true. So let's print out our value and confirm we have what's expected. So let's do make all /build client. And there we go. So the first thing it prints out is the type, which is a structure with 3 fields. And then after that, it prints out the actual values. Just as a quick aside, this syntax I use when printing it out is completely arbitrary and has really nothing to do with serialization. Like, you can't parse this string. It's just for debugging. Okay, so now what we could do is we could take our person, and instead of printing him out as a string, I wanted to actually serialize the person. And then I wanted to actually look at the individual bytes in the buffer, and we could kind of see how things are done. So let's think about this. So let's do, so I already have this buffer up here, which we're going to serialize to. And then to help us, I have this print buffer function, which is just going to print out the raw bytes in a nice way. So let's do C RPC status T status is going to equal C RPC value to buffer. We're going to provide it our value, the buffer size, and how many is written. So let's do size T written and written. Then just as a check, we want to confirm that this actually works. So we'll say if status doesn't equal C RPC success, we'll log fatal. Oh, do I not have log in here? Let's do, there we go. Log fatal. We'll say could not serialize. All right. And then finally at the end, let's do print buffer. And we're going to give it our buffer and not the buffer size, but rather written. So now basically we are going to print out the raw bytes that would in theory be sent across, you know, a socket or written to a file. And we're going to see if we could maybe decipher what's going on. So let's do that. Make all /build client. All right, so all right, this is a little dense, but so the first thing to be serialized is going to be the type. So this 0A, I believe resembles, or I believe signifies a struct type. Remember, a struct has a fixed number of fields, and we need their types. So after that comes the number 3, saying that our struct type is going to have 3 fields. 0 represents a byte, 9 represents a string, 9 represents a string. So this, in all of 5 bytes, we have serialized a full structure type. And the remaining bytes include the value. So let's think about that. So the value we would be expecting is going to be the age, which is 23, followed by Bob, followed by Alan. So, So we have the age here set. Remember, this is in hex, so 17 in hex is 23. So there's the age. And now all array types, or all types in my library which require kind of a underlying array, the way they're serialized is the length of the array is given and then the data. So a string, abstractly, in the case of the C RPC value library, is itself not an array. But under the hood, it's stored as a char star, which kind of is an array. So basically, we had Bob, which is 4 bytes in total, right, including the null terminator. So we have a 4 followed by 3 zeros. Lengths are encoded as 4 bytes, and this is a little Indian. So we have 4 and then 3 zeros representing the 32-bit value of 4, and then we have 4 characters. So I believe this should be Bob followed by the null terminator, and then we start the next string, which is Alan, which would be 6 characters, including the null terminator. So we have 6 followed by 3 zeros again, and then finally we have Alan followed by the null terminator. So again, the entire structure value was serialized only using 24 bytes, which is pretty amazing. If you watched my JSON video, you might realize that JSON is also a valid way of serializing. However, it is not nearly as efficient as doing byte-wise serialization because JSON is human readable. When we type out a number, we type out all the digits, which is extremely inefficient. When we type out a string, we have quotes at the ends, we have commas and brackets, which for the computer, for a person is very helpful, but for a computer is unnecessary. Okay, finally, before we move on to RPC, let's just practice deserializing the value, which is, again, kind of what the server would do when receiving a request. So now we have our buffer full of our serialized value, and we could do, let's think about this. We're going to do status equals CHRPC value from buffer. And what do we need to give it? I think we need to give it a, I'll say PDS for deserialization. And let's see, what do we give it here? Oh, we're going to give it the address of where we want to put the new pointer being created. We're going to give it the buffer, how many relevant bytes are in the buffer, and a way of determining how many bytes have been read. So let's do read in. Cool. And again, same thing here. Let's just exit if we fail to deserialize. So we could say could not deserialize. And let's think about this. Oh, at the end, we need to delete our new value we just created, PDS. And just to confirm that this worked as expected, we should be able to do CHRPC value print. And let's do PDS true. So if all goes well, we should have our original person value, which we have reconstructed just from the serialized bytes. So let's see if that is in fact what we have. Make all clear /build client. And look at that. It worked. We have the same structure type, and we have the 23 and Bob Allen strings. So deserialization worked as expected. With that, we could probably move on to actually using RPC. All right, so this is when things are going to get a little bit more verbose code-wise. So I wanted to start with writing the RPC server and then do the client. The server is kind of the more work-intensive part. I have a server file right now we're in, and it kind of has a lot of boilerplate for accepting connections over the network. We're only going to focus on a few parts. If you want to do this yourself, you can look at my GitHub and you can get all of this template code to set it up correctly. I'm not going to go into depth about it because it's not really that interesting. It's kind of just how to use sockets. So anyway, we're going to try to do this in one go. So let's see what happens. So the way this is going to work is that there is going to be a server state, and then we're going to have server endpoints. And whenever an endpoint is called, so a client makes a request, the endpoint is going to get a series of arguments, and it's also going to get the server state. So I thought for this example, the server state could be extremely simple. It could just be a queue, where we can push things onto a queue, and we can pop or pull from the front of the queue, right? So we're going to continue using the person example from earlier. So this is going to be a queue of people. We could think of a line of people, maybe waiting for, to purchase something online or something, or waiting to get into some sort of server for a video game. And to help us, I have taken our code from earlier and kind of consolidated it into a little person file. So basically, when we're in C, we're going to want to be using the person structure because that's easiest. When we do RPC, though, when we send a request back to the client, we're going to want to use the RPC value. So basically, you can create a person using this constructor, and you can convert it into an RPC value using this function, which is written just like very similar to what we wrote earlier in the serialization example. So with that, let's go. So let's first write our state. First of all of the endpoints are going to potentially execute in parallel. Our server is going to have a number of workers, and those workers will be responsible for kind of monitoring connections at the same time. So the point of this is that our server state is going to need to be synchronized. So let's give it a mutex, call it mute. And then we also want a queue, and we're just going to use a linked list. So let's do list t star queue. That's okay. We can include this. Include chutil list. Awesome. So now let's fill out the constructor and destructor for our server state, which should be pretty simple. So let's do log server state VSS equals log server state star safe malloc size of what's wrong? Call to undeclared function. What? Okay. Yeah, if you're unused to how I code, I usually have wrappers around functions that can fail. Malloc is very unlikely to fail, but it could. If it fails, it'll print out an error message and exit. It also keeps track of how many times we've malloced and how many times we've freed to prevent against memory leaks. That's a quick aside. So we can return our state, and now let's initialize the internals. So let's do safe pthread mutex init, and then we're going to do and vss mutex null. And then let's initialize our list. So vss q equals new list. Linked list and size of person t star. So okay. So again, this is going to be using my list type, which I have in like a utility library. Basically, you create a list by providing what implementation you want to use, in this case, a linked list. And then you also give it the size of each cell in the list. So this is going to be a list of pointers to people. Now, when we delete our server state, we need to be a little bit careful here. We'll say we assume no one is working on the state anymore. So we don't need to think about synchronization or anything. And we could do save pthread mutex destroy VSS and VSS mute. All right, now we need to delete the list. We need to be a little bit careful here because the list might not be empty. So let's do person t star star iter, and then we can say l reset iterator VSS q. Then what are we gonna do here? What are we gonna do? We're gonna say while iter equals l next VSS q. Uh-oh, what did I do? We are going to delete person star iter. And then finally, we're going to delete our list, VSS q. And then at the very end, let's think about this. We are going to say free VSS. All right, so that was a lot. The idea here is we are going to iterate over each cell. We have a pointer to the cell. The cell holds a pointer itself. So we're going to get back a pointer to a person. Okay, we iterate using an iterator, which will return null at the end. So we iterate until we reach null. And on each iteration, we delete the cell's contents. And the cell's contents is a pointer to a person. So we delete that person. Cool. Okay, now that we have our server state ready to go, we can start actually writing the behavior of each endpoint. So the idea is going to be very simple here. We're going to have an enqueue function and a dequeue function. Enqueue is going to take one person and push it onto the back of the queue. And what dequeue is going to do is it will, what it'll do is it's going to take a number of the number of people to dequeue, and it's going to return a list of people at most that size, all popped off in order from the front of the queue. So we have our functions, and their signatures are pretty large and maybe a little bit confusing. So before we actually fill out the endpoint, what we are going to do is define them here. So basically, there is a lot of boilerplate code, but at the very top, it defines how the server is going to be set up. There's a bunch of attributes, like, for example, how many connections at once the server can hold, how many worker threads there are going to be, when a client should be disconnected if they're unresponsive. 0 in this case means that they're never disconnected. So then after those attributes, you have to define what's called like an endpoint set, which is going to be a definition of each endpoint and the types they should expect to receive and return. So let's fill this out. So we're going to have new endpoint, new C RPC endpoint, VA. Okay, so our first one is going to be called enqueue, and it's going to take enqueue EP, and then we're going to have a return type. Now for enqueuing, we'll just say it doesn't return anything. It's expected to always succeed. Our queue has no limit, so yeah, we'll say there's no return type. So we give it null. And then after that, we give, in order, the argument types. So we expect, what do we expect? We expect a person, and we will, let's think about this. Okay, we're going to accept, you can accept multiple arguments, but just because we've used person as like one struct, we are going to continue in that style. So we are going to do new CHRPC struct type. So now we're not using the value constructors, but rather the type constructors, which just returns a type with no associated value. And this is going to have a CHRPC uint byte t CHRPC string t. Okay, so we'll say this is age, first name, last name. All right, so this is a good example of the enqueue function endpoint, or the enqueue function endpoint definition. Now we could do the dequeue function. So let's copy and paste this. Don't need that actually. So we're going to call this dequeue, and we're going to give it the, why is it not? Whatever. This is going to be the dequeue endpoint, and unlike the enqueue endpoint, this is going to have a return type. And again, we want to give, so we'll say that the only argument is going to be a byte. Oh, this is why everything's screwed up. Okay. Yeah, so we're going to say the only argument we're going to give the dequeue endpoint is number of people to dequeue. And then the return type, now it's going to be the same thing, but this is going to actually be an array. So we could potentially be returning 0 people if there's no one to dequeue. We could be returning 5 people if we ask to dequeue 5, and that's how many there are, right? So to do that, we really just do new CHRPC array type, and we're going to give it our structure type. There we go. So this is basically how we kind of define endpoints in my RPC library. Our next step is to actually fill out the enqueue and dequeue endpoints themselves and the logic that they will perform. Okay, so let's start with the enqueue endpoint. This should probably be the easiest. So enqueue is going to, let's think about this. We take one argument, and it's a structure which represents a person. So what we're going to do is we are going to, first of all, let's get our vlog server state. So every endpoint is given a pointer to the server state. So we're just going to cast it to what we know it is. Then let's think about that. Again, so people are going to be working on this queue in parallel. So let's lock mute, and then we can make sure to unlock at the end. Okay. Let's think about this. So why don't we say before, so again, we have this little person helper code, so we can make a person easily if we have the age, the first name, and the last name. Luckily, those are the exact things we do have, so we could say person t star p is going to equal new person. And let's give it, so again, we only accept one argument. So, okay. We're gonna do this one at a time. So we'll say uint un8t age is going to equal args 0. So the 0th argument, we only have 1, and we are going to get the value. Then we're going to go into the struct entries, get the 0th entry, and that as a byte. And we're going to do the same exact thing, but now for the first name and last name. So const char star fn is going to equal args 0 value struct entries. Now we get the first field, or kind of the second field in a way, and this is going to be a string. Let's get the last name, arg0 value struct entries to string. Finally, we can make our person by doing age, first name, last name. And at the end, we're going to, actually, we could do it right here. Let's do, oh wait, never mind, I'm sorry. Forget that. As a quick aside, I didn't really mention this in the serialization section, but this is kind of the way you kind of maneuver your way through the C RPC values. It's not really very safe, but the idea is that if you know exactly what type the value is, you can safely access the correct fields. So for example, if we did args0 value, I don't know, string, this would cause an error, right? Because our value we know is actually a structure, it's not a string. If we access it as a string right off the bat, that could cause all sorts of problems. Anyway, so we've created our person, and from here, we can push our person onto the queue in this critical section. So let's do lpush, and we're gonna do VSS Q and P. And that's really it. A few notes. We are not responsible for deleting the arguments. So when we enter the function, we're given an argument that lives on the heap somewhere. After we return, the server will delete all the arguments for us, so we don't need to worry about them. We're lucky that our new person constructor is going to copy first name and last name into new strings. Otherwise, there would be a use after free problem, right? Because once this function exits, the argument itself will no longer exist. So new person, the constructor, will take these strings which are originally inside the argument, copy them into new buffers before putting them on the queue. All right, now let's do DQ, which is going to be a little bit more labor intensive, but still not so bad. So let's take this, put it here, and we're going to copy and paste in the critical section also. Okay. So let's first figure out the number we want to DQ. So let's do un8t num to DQ, and this at first is going to equal the argument we provided, which should be args0 value b8. Okay, now we could also calculate the size of the queue so far. So we'll say qlen is equals llen vssq, and we can say if, I don't know, if the queue is less than the number to dequeue, we'll say the number to dequeue really should be the length. So this is the part where I was saying that we really return at most the value requested. If we request 5 people, but there's only 3 in the queue, we're going to return 3. All right, so now with that, we should be able to construct our array that we are going to fill with these people. So first things first, let's do C RPC value t star star people is going to equal PC value T star star safe malloc size of CHRPC value T star times num to DQ. Then we're going to do for uint8t I equals 0 while I is less than num to DQ I plus plus. And then what are we going to do here? We're going to have a okay. Let's first get the person we DQ. So we're going to do person T star P, and we're going to do Q poll. Not Q, I'm sorry, L poll. And P, I'm sorry, VSSQ and P. Then what we're going to say is people I is going to equal new CHRPC value from person P. Cool. Now because we're done with the person that we've popped off, we can do delete person P. Then at the very end, we are going to return at the very end, we are going to create the actual CHRPC array value. So this is an array of CHRPC values, and what we can do is we can say if num to DQ is greater than 0, we can do star red is going to equal new CHRPC n empty composite array, I think. Yeah. And this is going to take people num to DQ. We'll say otherwise. Star red is going to equal new CHRPC type. Let's just let's take this. Let's do new CHRPC composite array. There we go. All right, so this is a little bit nuanced here. So basically, there are two constructors for creating a composite array. There is an empty array constructor and a non-empty array constructor. The point here is that if the array isn't empty, the type of the array can be inferred, right? Because we can read the type of each cell and confirm that they match, and that cell type will be the used to create the overall array type. Okay, if we had no entries, if I just said I have an array of nothing, there'd be no way to tell if it's an array of integers or an array of strings or an array of, floating point numbers, right? So when we create an empty array, we provide the type. That's the point of that. Let's think, is this correct? If the number to DQ is 0, this still should be okay, because safe malloc should return null in that case, but we can still do safe free down here of people. In this case, the ownership of people is transferred to the array that's created. And lastly, this design where we do star red equals the return value, the idea here is we're not actually going to return the value using the return keyword. We just write it to a specific location, and then the server understands to interpret that as the endpoint's return value. The actual value that is returned by the endpoint is a command of whether to keep the requesting client alive or not, which is another thing that's maybe not really that important for this video. Okay, finally, we can do the final part of this video, which is just writing the client. I'm not going to go too crazy about making the functions perfectly abstract away RPC. You could, when I show you this part, you could totally understand how to make that jump. I'm just going to do it in the simplest way possible. If you made it this far, thank you so much, and I hope you enjoy the end. So basically, similar to the server, the client program has some boilerplate code too that I am not going to go over. But after creating a client, you can use the client to make C RPC requests. So let's give it a go. So what we're going to do first is try enqueuing data. So let's do status equals C RPC client send request variable arguments. We're going to give it the client. We're going to give it the name of the function. So let's first try enqueue. And now normally would give it the address of where we want the return value to be placed. For enqueue, there is no return value, so we could do null. And now we need to give it the argument. Unlike a lot of calls in this library, the arguments are not consumed by this function call. So after we make the call, we need to delete the arguments. This way you could make multiple requests with the same arguments without having to like recreate them all the time. So let's do C RPC value t star person is going to equal new C RPC value struct. Oh, no. Struct value VA. Okay, now what we're going to do, same as before, new C RPC B8 value 23. New C RPC string value Bob. New C RPC string value Alan. Now we're going to give this as the argument for person. We are going to delete our value at the end, person. And let's say if status doesn't equal C RPC success, log fatal. I could say request failed. All right, perfect. So let's try this out. Let's try enqueuing a few people, and then we can try the dequeue function to confirm that that's also working. Okay, so now I have two terminals. One's going to be the server, one is going to be the client. Make all. Let's get our server started up here. Also, I added some logging to the server, so when we do enqueue someone, it should print something out. Now let's do build client. There we go. We can see we have Bob Allen enqueued, printed out from the server, and our client exited. Now dequeue is going to allow us to dequeue multiple people. So why don't we enqueue multiple people? So let's do 53. We could say Dale Smith. And let's enqueue this guy. Build client. Dale Smith has been enqueued. And let's try Jessica. I don't know, Jessica Moob. That's a funny name. And Jessica is, I don't know, 64. She's pretty old. Make all. /build. Client. Bingo. Jessica Moob has been enqueued. So now let's try out dequeue. So what we're going to do, let's comment this out just in case we want to use it again later. Probably won't. That's okay. Now let's do C RPC value star people. And we're going to say status equals C RPC client send request VA. We're going to say client. We're going to call the DQ function, and we're going to send the output to people. And we are going to, let's think about this. Oh, we do have an argument. T star num to DQ. Let's start with 1, so new C RPC B8 value, 1. Num to DQ. And then down here we need to delete C RPC value, num to DQ. Finally, we can do same thing if the request failed. Do that. Now, for the moment of truth, oh, let's do this preemptively. Delete the value people. Let's print out all the people we dequeued. So for un32t, I equals 0. Well, I is less than people value array len I plus plus. All right, this is when things are going to get a little bit verbose, say the least. So let's do printf first name %s. Then we're going to do last name %s. Finally, let's do age %u. Again, so we are going to need to use the weird C RPC value way of getting to the actual internal data. Again, if we're gonna do this entirely how RPC would normally be done, what we would do is we'd have our own functions called NQ and DQ, and they would be responsible for sending the request. We're not going to do that right now just because this video is already probably an hour long, so I thought I would just print out the values and call it a day. So the first name will be people value array entries I. Then, here we go, struct entries 0. Uh-oh. First name is the first, I think. All right. Now let's do this again. Uh-oh. 2. And then finally the age. So this would be B8 and this would be field 0. And it expects an expression. Why? Oh, here. All right, so moment of truth. Can we dequeue someone from the queue successfully? Let's do make all /build client. Look at that. And it even says dequeued one person on the server. I added that log message. Now let's try 2 people. Make all /build client. There we go. There we go. We got Dale and Jessica. And if we tried this again, I think nothing would happen. Let's hope. DQ'd 0 people. Awesome. So, again, if you made it this far, thank you so much. I worked really hard on this project, so I hope you found it interesting. Again, if we wanted to make this like full tier RPC, we would have our own function called NQ and DQ here, and maybe they'd take the client and do all the work for us. But that's it. So thanks for watching, and hopefully I'll have a new video soon.